Hi everyone, my name is Vanella. I'm part of the J2 team here at the Texas Advanced Computing Center, and today we will be running through a tutorial on the basics of AI/ML and data science. This is a great course for anyone who has been using the Jetstream system, who knows Python, but is interested in learning AI/ML. This starts really at the basics, and then we'll work our way up through this tutorial. So I'm very excited to jump into it today. So in the links of the training, you will find a um, J2 tutorial workbook. And so we will be starting in that workbook. It has a few pieces of code pre-written into it, but we will go ahead and we will start with that. So, okay, so here we have our J2 AI Basics workbook. And so what you'll see there, first of all, is a bunch of pip install statements. This is how we download modules and packages through Python. So Python has some inbuilt functionalities, but other members of the community and Python developers have built specific libraries and modules which will help us make things a little easier. So you can go ahead and just hit run on those statements. So it'll download all of those features as well as these many, many modules that we need to be able to do today's workshop. All right, so once that you've run those, you'll see that they've all installed and it should be all good. And then the first thing that we'll get started in today is with linear regression. So linear regression, think y equals mx plus b. So if you have a line, you're looking to define the slope and intercept of that. And so without doing it without a calculator or whatever, we can do it in Python. And so the first thing that we will need to do for that is to go ahead and read in our data set. You'll see that the data set files are also linked as well as access to GitHub. So you can either download them and use the file path through your computer, or you can download them from GitHub directly. But I have them on my Jetstream instance, so that's just how I'm going to do it today. So what we're going to do is we're going to start with creating a data frame. So today we're going to be looking at study data. So what that data frame, we'll just go ahead and call that study. So study DF. DF means data frame. So we're going to use our pandas library, which is a very, very common machine learning AI/ML library to use. So we're going to use that to read in that CSV from that file. I have my file path just copied off to a side here, so I'm just going to go ahead and grab that. All right. And then we want to be able to take a look at maybe the first 5 rows of that data set. So we're going to do study df dot head 5. So what that'll do is that will give us the first 5 rows of that data set for us to look at and see what it is. So we can either run from here, or you can also hit Shift Enter within your notebook to see. So here we can see that the data set was written properly, and we can see someone that studied 2.5 hours got a score of 21, someone who studied 5 hours got a score of 47, all the way up to someone who studied 3.5 hours and got a score of 30. So now what we're going to do is see if we can, explore the data a little to get a little more context into this data set. So we're going to do study underscore df dot describe. And so what that does is that gives us all sorts of statistics about the data set that we're looking at. So we see there's a total of 96 hours and 96 scores. So that means there are 96 students that we're looking at. The mean number of hours studied, the average score, standard deviation, max, min, percentiles. So it's just great to give us a range and a little bit more information about the data set. This is a small data set, so we could look at it ourselves, but as things get more complex, you'll be looking at larger and larger data sets. So this is a great way to condense all of that information all at once. All right. And then another way to look at this data too is visually, right? Some people like to look at numbers, some people are visual learners. So there is another library called Seaborn in Python, which is a great way, it's a great library that has a ton of visualization tools in it. So one thing that we're going to use is we're going to plot the data here. So then we'll do SNS, which is Seaborn, dot displot study underscore DF. And then we want to look particularly, let's just look at the scores. We got to make sure that we capitalize accordingly because that does matter. And then we close our parentheses. This takes the time to run, but we can see the distribution of scores throughout, right? We can see the number of students who are scoring roughly between 90 and 100, where the majority of students are. So we see a lot of students who studied probably who got between around 65 to 82, or maybe 75 to 82. In that space, we also see another jump around maybe 25 to 35, 40 as well. So just a great way to get another picture of the data that we've got. And when we always think about linear regression, right, we think about that slope line. And so we can also use Seaborn to do the same here and plot all of our data points. That'll give us a rough slope line. So we know what to expect. Would we expect it to be positively correlated, negatively correlated? So I think that's another thing that's great to look at. So we'd use sns.lmplot, and then we want to look at hours as our x variable, and then y as our scores. Once again, capitalization matters. And then the data that we're going to be looking at is study underscore df. And then we will give that a go. All right. So here then we can see hours versus scores. So it's positively correlated. We'd expect that someone who studies more hours is going to do better on the test. So that means we would expect a positive slope during our equation as well once we do that. So now that we've kind of done the data exploration, let's get into actually being able to plot and predict this equation. So first thing we're going to do is we're going to split our data sets. We want to be able to look at our X column and our Y column separately. So what we're going to do is we're going to take X is study underscore DF. Because it's a two-column data set, we do things a little differently than we do with larger data sets. So we have to use this function called iloc. And then what we're going to do is we're just saying here that we only want the first column, right? Columns in Python start at 0. So we really only want that column number 0, right? Oops, I meant to add another thing in there. And then we want to do our Y as well, right? And that'll be study. Oh, I have an extra space here. It's on me. Study underscore DF. We're going to do the same thing here, but since our Y is the second column, we're going to say that we want our second column, which is 1. Ooh, I put my parentheses in the wrong, there, my ellipses. All right, so now we're going to go ahead and run that column, and then that column is run. We could print out X and Y, but we know it's there. So now what we're going to do is one of the basics of AIML, which is a training test split. So whenever you have a data set, we want to split our data set roughly into an 80-20 split, 80% being training data and 20% being test. Why do we need this split? So test data is what'll tell us how accurate our model is, right? If we don't have the answer of what did this student get and we go to predict, we don't know if that prediction is right or wrong. So that's what that test data is for. Why it's an 80-20 split roughly is because we want to have a larger training set, but we don't want our test set to be too small. And this can always be adjusted based on the data set that you're using or something else, but this is just typically the split that is most often used, is an 80-20 split. So now, how are we going to split this data? So we're going to say X train, right? So this is our that's our training data for our X. And then we want X test, right? That'll be our training data for test. And then we do the same with Y. Y train, Y test. And then we're going to use a function called train test split, very aptly named function, to split our X and our Y into the test size. We want it to be 0.2 or 20%. And then we use this function called random state. So we want to get the same training and test split every time so that we have repeatable numbers. So we'll set a random state and you can just choose any number for it. I'm going to choose randomly 42. So now we run our training and test split, and now our X and our Ys are split into 80/20s. All right. So moving on to the next step. Now that we've done all this data exploration and finally split our data, it is time to train our model on this data. So what we're going to do is we're going to create an instance of our linear regression model. So regression. So we create our linear regression model and we've instantiated that. And then what we're going to do is we're going to fit our model to our training data. So X train and Y train. And sometimes those can take a minute, but since this is a smaller data set and smaller model, we got our linear regression. So let's go ahead and we'll see just roughly what is the equation that we're getting out of this. So we're going to write a print statement here. So we're going to do y equals, right? We're going to do our reg dot coefficient. So what we're doing there is like from this this linear regression model that we've named reg, we're going to get our coefficient, right? Like what is the positive or negative amount we expect things to increase. We're going to get that. And we get our reg coefficient. We want to turn it into a string for the sake of the equation. Plus, we need our x, right? You don't have to format it to look this pretty, but for the sake of this, I will. I know all these string statements can be a pain sometimes, but hang with me. And then we're going to get our, and then we're going to get our intercept, right? What is the starting value? So we get our intercept, underscore, and then we're going to hit enter. It says I forgot a comma. Let's see where I forgot a comma. I think I forgot a plus right there. All right, so there is our equation. So that here we see that our equation is roughly y equals 9.8x plus 2.4. Our intercept being 2.4, and that on average, we would expect your score to go up about 9.8 points for every additional hour of studying that you did. Right, so that's the equation that the model gave us. And so now let's see how accurate this is, right? This is the part of why we use our training and test data. So what we're going to do is we have a really great module imported, which will help us use something called an R-score. An R-score is basically a percentage of how accurate the model is. So here we do R-score.reg, reg score, and then we want to look at it on, let's look at it both on our training and our test data. So let's start with our training data. Train, Y, train. And then we're going to, all right, enter. And then we're going to print, lowercase, print our R2 score times 100, because we want it to be a percentage instead of a just a number, a decimal. So we're going to print that, and we're going to see that on the training data, right, this model's about 98% accurate, which is fantastic. Just for reference, usually in industry, a model that is 70% accurate or above is considered great scores. So this being 98% means that we have a pretty good model. So that's on our training data, but now we want to see what it does on our test data. So we can, we'll make our lives easier. We'll just copy and paste this one, and then we'll change X train to X test and Y train to Y test, and then shift enter. And that we see even on our testing data, these scores are about 97% accurate, which is great. If a model has a really high score on its training data and a really low score on the test, it means you've overfitted that model to the data set. And then if it's got really, really, really low scores, maybe you've underfitted it a little too much. So this means that right now we have a really good model that is fitting really well with our data. So why don't we look at this once again in a more visual form? So what we're going to do is we're going to convert some of these into the prediction. So y pred underscore test. So this is the predicted values that the model gave us for the testing data. And so we do reg dot predict, which means we want the model to predict these values based on x underscore test dot values dot reshape. We do this part because once again, it's a little weird because it's a 2-column data set, and we want to make sure that at the end the columns are reshaped to be 2. And then okay. And then we're going to do y pred train equals reg dot predict x train dot values dot reshape. One. All right. We're going to get an error here because we're not printing it out, but rest assured that data is being fitted. Okay. And now what we're going to do is we're going to turn all of this into a plotter chart, a scatter plot. So what we're going to do is we're going to plot our X train and our Y train along with our Y pred train numbers to see how that looks like. So we'll use plot.scatter to create the scatter plot. And then we're going to plot X train and then Y train. And you can use any color. So color, I just want to use black for this. All right. And then we do plot dot plot. And then we're going to look at X train and Y pred train in the color green. And you can choose any color here. And then I'm going to set line width. So I set line width just to be a little thicker. That way we'd be able to see it. And then we're going to do plot dot show. All right. Well, give a moment for the computer to think. Sometimes these charts and graphs can take a minute, but all right, here we can see that our green line is the slope of what we got from our Y pred, and versus the scatter dots, right, which are the black points, which is our actual training data. So we see that this line is pretty dead center of all of those points taking into account. So that shows that our model is decently accurate, and it just gives us a better visual representation of that, right? And so we can continue on looking at some of these things. Here we can look at for, our test data, basically. We can do the same thing, right? So we'll, once again, do a little copy and pasting to make our lives easier, right? And so we want to use our test data this time. So we do X test, Y test, X test, and Y pred test. Why don't we use some different colors this time? I think we keep the dots black, but why don't we use a blue line this time, right? And if you want to make your charts neater and nicer, we can always add 9. Fix that line with 3. We can always add, say, a title. So plt dot title, and we say linear regression, actual versus predicted. You can also add axes. You can also add axes. So plt.x label, and our x values are hours. And then plt y label, which are our scores. All right. And then we run that. And once again, you can see the actual versus predicted. There are fewer lines here because remember we did an 80-20 split. So the other 20% are on this chart. So, all right, that is our linear regression section. Next, we're going to be moving on to polynomial regression, which will be the next video. I'll see you there.